Assalamualaikum warahmatullahi wabarakatuh and good morning. So for first lecture regarding the Vehicle Powertrain Management Systems or VPMS, okay, we will start with first chapter that I mentioned before. The powertrain consists of engine and transmission. The word management means that how to control these systems. Okay, nowadays, modern motor vehicles are fitted with a wide range of electronic and computer control systems. So why we need to use electronics and computer control in vehicle system? We need to improve the operation or efficiency of an existing mechanical system, whereby nowadays the electronic components are more affordable, smaller than in the past. Another reason is we want to reduce the vehicle emissions and also to improve the vehicle safety. It also, we have a demand from customer. For example, there are a lot of electronic systems such as ABS, which is anti-lock braking system. We also have climate control, where we can control the air conditioning inside the vehicle with electronic control. Other than that, we have to control the electric seat adjustment system and etc. So now we go to the electronic systems or computer control systems. The electronic systems uses electronics to improve the safety, size, cost or efficiency of a system, but the electronics do not necessarily control the system, and the system can be manually or automatically controlled. Here there are three figures. Figure 1.2 shows a headlight circuit that is switched on by the driver when the light switch is turned to the appropriate position. When the switch is in the correct position, it allows electric current to flow from the battery direct to the light. Okay, next figure 1.3 shows the light circuit fitted with a relay. When the driver turns the light switch to the appropriate position, it allows electric current to pass through the relay, and then the relay will be energized. So when the relay energized, the relay contacts are forced to close, which then allows a larger electric current to pass from the battery through to the light bulbs. Then figure 1.4 shows almost the same wiring circuit as figure 1.3, but the relay has been replaced by an electronic module. The electronic module performs the same task as the relay, but does not contain any moving parts. For example, there are no contacts and no electric internal switch. The module can consist of very few simple electronic components such as transistors and resistors, which are inexpensive and more reliable. So next, what is computer control systems? The function and the action of the computer control systems are automated and use a computer or ECU to control the actions and the functions. Figure 1.5 shows a headlight circuit. Okay, for example, a headlight circuit whereby a light sensor has been included between the light sensor and the electronic module. In this example, the sensor simply forms part of the circuit between the main switch and the electronic module. Therefore, if the light switch is in the on position, the light will be switched on. Okay, and then this type of system would not represent a fully computerized system. Next, figure 1.6 shows a similar circuit whereby the electronic module is replaced by a more sophisticated computer module or ECU. In this example, the light sensor is directly connected to the ECU and provides a signal that varies the amount of light. Okay, for example, the voltage generated by the sensor could increase or decrease as the light reduces. So the computer would then effectively make the decision as when the lights were switched on. ECU control system. Okay, ECU receives information from sensors, makes calculations and decisions, and then operates an actuator or provides signals for other electronic components such as digital displays. Figure 1.7 shows the basic principle of almost ECU control systems, whereby a sensor produces some form of electrical signal which is passed to the ECU. The ECU uses the information provided by the signal to make appropriate calculations and then passes an electric control signal to an actuator or digital component system such as dashboard display. Figure 1.8 shows a more complex arrangement of the ECU. This example would be typical for fuel injection system, whereby the ECU is controlling a number of actuators and whereby a number of sensors are used to provide the required information. Okay, what inside the ECU? So there are several components inside the ECU. First, we have microprocessor. ECU may contain one or more microprocessors, which are the main decision-making components. It will provide an appropriate output signal, which is used to control an actuator or influence another systems, usually by communicating with other ECU. Second, we have amplifier or driver stage. So the microprocessors operate using very weak signals in 5 volts or current range from 0.5 to 1 ampere. So would not be directly connected to the actuators. So it need to amplify the voltage and currents so that the actuator will use or get higher voltages and currents. So figure 1.11 consists or shows a modern ECU and the components. Okay, figure 1.12 shows the essential functions within the ECU and the essential tasks of the microprocessor. Meanwhile, figure 1.13 shows a simple circuit whereby a light bulb is switched on okay, or off using a power transistor. Please be noted that the transistor is switching the earth or return part of the 12-volt circuit. The transistor receives a signal from the microprocessor and effectively emulates or copies the signal onto the 12-volt circuit. Okay, in the modern ECU, it is often in switching a circuit on and off at very high speed and frequency. For example, in ignition coil or fuel injector, the switching process may occur as often as 100 times per second. Next, there is a memory inside the ECU. Okay, for example, in ECU, they are the EEPROM, okay, erasable programmable read-only memory, or EEPROM, electrical erasable programmable read-only memory. And then all the operating data and also the controlling programs are stored in ROM. Okay, whereas instantaneous data, for example, engine speed, load, or temperature are stored in RAM. Arithmetic Logic Unit, or ALU. The ALU is a part of the ECU that handles all the calculations the ECU needs. Okay? It performs arithmetic and logic operations, including bit shifting operations. So, in generally, the LUs perform three types of operations, which are logical operations, bit shifting operations, and also arithmetic operations. Okay, then for input from sensors, there are normally two types of signals. Okay, one is analog signal and another one is digital signal. An analog signal can be regarded as a signal or indicator that continuously changes from one value to another. And then voltage signal produced by many sensors can be an analog signal. For example, throttle position sensor. Meanwhile, a digital signal provides a step or pulse signal. Okay, figure 1.15 shows the example of analog and digital signals. Okay, for A is an example of digital signals whereby the pulse could be used to provide speed or frequency information. Meanwhile, for B, the analog signal, okay, on top of the 1.15B, on top is the analog signal, and then below one is the digital signal, whereby it has two thresholds at 9 volt and 3 volt. When the voltage is rise above 9 volts, okay, it converts to digital signal from 0 to 12 volts. And then when the analog signal is below than 3 volt, it converts to digital signal from 12 volt to 0 volt. Okay, and then figure 1.15C shows the principle of analog to digital converters, whereby the conversion is done inside the ECU, okay, to get the digital signal. as an output. So this is an example of the programming related to analog to digital conversion. Okay, the analog to digital or AD converters. Okay, so ECU ideally require a digital signal. Some form of conversion is necessarily to change the analog signal from a sensors to the digital signal. Okay, the sensors that produce analog signals need to be converted to digital signal for the microprocessor to function before the AD converter is used. Okay, in ECU also contain converters, which is a DA converter, where it change the digital signal into the analog signal that might be beneficial to the actuator to operate. For example, fuel gauge that using the analog signal. Okay, the construction of the analog to digital converters is shows here. Okay, so in summary, the complete ECU receives information from sensors that might be digital or analog signals. Okay, the digital information passes directly to the microprocessor, but the analog information must be converted to a digital signal before being passed to the microprocessor. Next, microprocessor assesses the information, perform calculation via ALU, okay, that refers to the program memory to find out what task to perform, makes the appropriate calculations, and pass an appropriate control signal to the relevant actuator. Okay, when the actuator is operated using higher voltages or higher currents, the weak digital signal from the microprocessor need to be amplified using a power transistor or relay. So the essential point to remember that the ECU cannot achieve its main objective, okay, which is to operate an actuator or electric component unless the appropriate signals are received from the sensors. So this is the example of the complete ECU. There are several sensors that send signals to the ECU, and then ECU calculate or manipulate the signals to give the output signals to several actuators. Okay, for example, when we look into the engine management system or EMS, there are a lot of sensors and also a lot of actuators. So you need to know what sensors involved, the location of the sensors, the function of the sensors, and also where is the actuators inside the EMS. Okay? What is the function and where is the location of the actuators. So there are several sensors that could be fitted to EMS. For example, we have engine coolant temperature sensor. We have air temperature sensor at intake system. Okay. We have a MAP, manifold absolute pressure sensors. Okay. The function is to indicate the engine load. Okay. And then we have a crankshaft position sensor, camshaft position sensor, throttle position sensor, boost pressure sensor, lambda sensor 1 and lambda sensor 2. Okay. In terms of actuators, we have fuel injector, solenoid, for controlling the field quantity, we have idle speed stepper motor for controlling the idle speed. We also have EGR or exhaust gas recirculation. If the vehicle has turbo, we have a turbocharger wastegate, solenoid valve, and also ignition cord. This is the common of the almost of the vehicle. So normally in EMS, these are the parameters that need to be measured in terms of temperature, movement, position, pressure or vacuum, and also oxygen. So figure 1.16 shows a means of providing information of sensors and also the application of each sensors. So thank you for today's lecture.